Good day everyone, I am Juveline Onto. So this is the continuation of my topic. My topic is all about pseudogenes. So before we go along, we need some recapitulation about my topics. My topic is pseudogene, which is the segmental DNA structurally resemble a gene but it's not capable of coding for a protein. So there is the protein coding gene A, which is it has a promoter, and pseudogene that is don't have a promoter. I introduced to you the processed pseudogene and also the unprocessed pseudogene. So the processed pseudogene, that is the consequence of retrotransportation, that is lack of promoter element. So while the unprocessed not produce functional protein or might produce protein which having different function. And I also introduced to you the centromere, which is that helps the cell divide up its DNA division. Also the human genome variation, the gene from ancestral that inherit every person from their ancestry, like color, skin, and also the hair. So let's move on. Let's go to the next topic. Let's proceed in segmental duplication in human genome. Approximately 5% of human genome is composed of regions of segmental duplication that have formed relatively recently in evolutionary time. Segmental duplication are regions of 1,000 or more base pair with DNA sequence identity of 90% or greater that are present in more than one copy but are not transposons. So dito inappropriate recombination between the duplication sequence. So example, in the genomic regions proximal to centromere and telomeres are enriched with segmental duplication. So as you can see in the chromosome 7, that is the example of appearance, which is the segmental duplication within region in human chromosome 7 give rise to William Burren syndrome. So as you can see, we have here the A and B. So the A, that is the inappropriate combination between duplication sequence, cause the deletion of the region of the chromosomes, while in letter B, William Burner is rare congenital syndrome disorder that is characterized by outgoing personality in facial appearance like moderate to mild intellectual disability and range of physical problems. So that is the example of segmental duplication. I have here the animal gene, which is it has inactivation and increased gene dosage and also the sub-functionalization. So the example is the ancestral globin, which is it has alpha and beta globins and also the myoglobin and cytoglobin and also the neuroglobin. So that is the example of animal po. The next part, that is the variation in centromere organization among species. So in budding geese, autonomous centromere sequence specify protein binding site required for assembly of kinetochore. It inserted into cellular DNA molecules, which is the plasmid. So they under them capable of interacting with the mitotic spindle and segregation during the mitosis, as I presented to you last meeting the video. So this is the budding yeast centromere in the screen. As you can see, in the uppercase present in at least 14 of the 16 centromere, and the lower case that is present in at least 9 centromere. So if any base can be presented in the picture. As you can see, there is part A and also B and also the C. So in letter A, we have here the replication during the mitosis and having a random segregation. So as you can see, we have here the conserved DNA element, which is the 1, 2, and 3, which is under the white colonies. So dito sa letter A, that is the abundance of nucleotides and its overall length. With B and C, that assay for mutation stability of a plasmid that is used to clone centromere from most budding yeast chromosomes. So the plasmid carries a gene encoding an enzyme that is involved in adenine metabolism. So when the plasmid is present, colonies are white. So if the plasmid is lost, the colonies become red, as you can see in the random segregation. As fault of the accumulation of a metabolic byproduct. So the plasmid is capable of replication but lack of centromere. So the colony is mostly red, reflecting in the efficient of segregation. Plasmid at mitosis. If the plasmid becomes functional, it has centromere. So the colonies will be white as the plasmid will be successfully transmitted at nearly division. In organization of the centromeric DNAs of budding yeast, fission, and fruit fly. As you can see, we have there the A as cerevisia and the B, which is as sperm chromosome third, and C, which is the melanogaster X chromosomes. The cerevisia or the Saccharomyces cerevisia is a species of yeast or single-celled fungus microorganism known since early times of its fermentation properties, which is it can make wine. And the second one, that is the palm chromosomes third, which is the Schizosaccharomyces palm genome is approximately 14 MB, of which about 12.5 MB is unique sequence. The genome organized by 3 chromosomes: central core, inner repeats, and outer repeats, which is represent the yellow, pink, and the blue, and also the violet. So in letter D, that is the melanogaster, which has X chromosomes, or Drosophila melanogaster, with male have one X chromosomes, whereas female have two. The resulting of imbalance in gene dosage is corrected by increased expression so from the single X chromosome of male, a process known as the dosage compensations. The last topic I had, which is the vertebrate centromere DNA, is an essential component of the chromosome that is required for accurate segregation of chromosomes during mitosis and meiosis in eukaryotes. So its function includes sister chromatids, cohesion and separation, and microtubule attached chromosomes movement, and mitotic checkpoint control. That would be all. Thank you for listening. Have a great day, everyone.